Welcome to the Deep Dive, where we extract the crucial insights from the latest AI research. Today, we're dissecting a really interesting paper. It tackles a core challenge in using CLP, especially for few-shot learning.
Right, particularly in those tricky technical domains like AI research itself.
Exactly. CLIP is amazing at connecting vision and language, but sometimes it kind of stumbles.
Especially when it has to tell similar categories apart with just a little bit of data.
Yeah, that inter-class confusion. It can really slow things down.
It definitely can. I mean, CLIP's strength comes from its broad training, that contrastive learning on huge image-text data sets.
So it wasn't really built for super fine-grained classification from the start.
Pretty much. So in few-shot situations, and especially if the domain is a bit different, that ambiguity, it becomes a real bottleneck.
Which brings us neatly to the paper. Logits DeConfusion with CLIP for few-shot learning by Shu Lai and colleagues. They're tackling this head-on.
Yeah, it's a very targeted approach. They basically pinpoint this confusion happening in CLIP's output logits as the key problem for few-shot.
And their method is called Logits DeConfusion, or LDC.
That's the one, specifically designed to deal with that problem.
Okay, so for everyone wanting the quick version, the key takeaway in under a minute, this deep dive looks at Logits DeConfusion, LDC. It's a new way to basically squash the problem of CLIP getting confused between similar classes when it only sees a few examples.
It uses a smart module called Multi-Level Adapter Fusion MAF to get better image features.
And then there's the Inter-Class Deconfusion module, ICD. That one actually learns what the confusion looks like and removes it from the logits.
Right, and the bottom line is it leads to significantly better accuracy in few-shot classification.
So our mission today is to really unpack LDC. We'll look at MAF, ICD, how they work together, and how effective it actually is.
We'll get into the architecture, the mechanisms, and what this might mean for few-shot learning research going forward.
And definitely highlight the performance gains they saw.
Okay, let's dive in. Why does CLIP get so, confused with similar categories in few-shot learning?
It really boils down to its pre-training. It learns by contrasting images and text, right?
Finding the connections.
Exactly.
Yeah.
Which is great for zero-shot stuff, that broad understanding, but it doesn't explicitly push the model to draw sharp lines between, say, two very similar types of bird in a classification task.
I see. So the objective wasn't fine-grained separation.
Precisely. And you can actually see this in Figure 1A in the paper, the initial zero-shot predictions. They show quite a bit of overlap for related classes. It's like trying to tell similar dog breeds apart instantly with just one picture each.
It gets the dog part, but maybe not the subtle differences between a Labrador and a Golden Retriever immediately.
That's a good analogy. And this gets worse if the new task, the downstream task, uses data that's different from what CLIP saw during pre-training.
Domain shift. Right. Those domain differences mean the features CLIP learned might not perfectly capture the really important nuances for the new categories.
That makes total sense. If it hasn't seen many examples, especially visually similar ones from this new domain, setting clear boundaries is tough.
Absolutely. The paper points out this really undermines classifiers you try to train with just, a handful of samples.
Because any uncertainty in the base model just gets amplified when data is scarce.
Exactly. It's much harder to learn reliably if the starting point, those initial predictions, are already a bit fuzzy between close categories.
Okay, problem defined. Interclass confusion in CLIP for few-shot. Let's get into their solution. Logits DeConfusion, LDC. What's the big idea here?
The core idea is pretty elegant, actually. They want to explicitly model the confusion, learn what it looks like, and then subtract it out.
Model it and remove it, instead of just fine-tuning everything.
Yeah, exactly. It's more targeted. Think of it like proofreading. You don't rewrite the whole essay, you just fix the specific typos or awkward sentences. Here, they're fixing the confusion in the logits.
Okay, interesting. But how do you model something like confusion? That sounds a bit abstract.
They treat it as an additive noise term. They call it IS, delta S. This noise is basically messing up the clean initial zero-shot logits, which they call SZSI.
So the goal is to estimate this is noise.
And subtract it. To get cleaner logits, IS. Figure 1B in the paper shows this. Visually, you see a clearer separation between classes after they do this.
And logits are just the raw scores before the final decision, right? Higher means more confident.
That's right. Raw scores for each possible class.
Okay. Estimating the noise ass. How do they actually learn to do that?
They introduce a learnable module, E delta. It takes two things as input. those original zero-shot Logits, SDSI, and also the image features themselves, EIS.
Ah, so it looks at the initial prediction in the picture.
Exactly. The idea is that by seeing both, the module can learn to spot patterns that signal confusion between classes. The image features give context.
Like using the visual evidence to figure out where the prediction might be shaky.
Precisely. The visual features can help it figure out, okay, based on this image, these two classes are often confused. Now, to train this E module and the whole system, they use specific loss functions.
Right, the training objective. Let's talk about those losses. How do they make sure the deconfusion works well?
Well, the main one is standard cross entropy loss, LCE. That's calculated between their cleaned up Logits, U, and the actual correct label, YI.
Makes sense. Got to make sure the final prediction's right.
Yep. But they also have something called a similarity loss, ILSIM.
ILSIM, what's that for?
That's really important. It uses L1 regularization to make sure the clean Logits don't drift too far away from the original zero-shot ones, SESI.
Ah, so it stops it from over-deconfusing? Like throwing away CLIP's original knowledge?
Exactly. You don't want it to forget everything CLIP learned and just overfit to the few examples you have. It's a balancing act.
Reduce confusion, but keep the useful prior information.
That's the goal. The total loss, L, is just a combination of the cross-entropy loss for accuracy and the similarity loss for regularization, basically. Figure 1C gives a nice overview of this whole LDC modeling process.
Okay, got the core concept. Model the confusion as noise, learn to estimate it using Logits and image features, subtract it, and use losses to guide it. Now, the architecture, they mentioned 4 bits: zero-shot, CLIP, MAF, ICD, and ALF. Let's start with MAF multi-level adapter fusion.
Okay, MAF. This module is all about getting a better, richer feature representation from the image before you even get to the deconfusion part.
Better features how?
Well, the authors realized that different layers in CLIP's image encoder capture different kinds of information, right? Early layers see textures, edges.
Low-level stuff.
Yeah, and later layers get the more abstract semantic meaning, high-level concepts. MAF's goal is to harness all of that diversity, not just the final output. They think this helps make the model more adaptable for few-shot learning. Figure 3 shows the details.
So instead of just one view, it's getting multiple perspectives on the image.
That's a great way to put it. And it does this using a few parts: multiple side adapters, a fusion mechanism, and a projector.
Side adapters, what do?
They tap into features from 4 different levels of the CLIP image encoder. Each level's features go through a small, lightweight adapter module.
And these adapters are learnable.
Yes, they're small, learnable bits that help fine-tune the features from each level, making them more useful for the specific task you're adapting to.
Okay, so each level gets fine-tuned. Then how are these different adapted features combined? The fusion part.
Right. They tried 2 main ways for fusion, shown in Figure 4. First is weighted fusion, WF. It's simple, just a weighted sum of the features from the 4 levels.
Like giving more importance to certain layers.
Yeah, they even tested specific weights, 0.1 for the first, 0.2, 0.3, and 0.4 for the last, and also just equal weights, 0.25 each.
Okay, straightforward. What was the other fusion method?
Learnable fusion, LF. Here, they concatenate the features from all 4 levels.
Put them together.
And then pass that bigger feature vector through another adapter. This adapter learns the best way to combine them and reduces the dimension back down.
So it learns the fusion strategy itself?
Exactly. Using the same kind of adapter structure they use elsewhere, typically linear layer, RILU, batch norm, another linear layer. You can see that general structure in Figure 2.
Got it. Weighted or learned fusion. What about the projector you mentioned?
After fusion, the combined features go through a frozen projector. What it is depends on the CLIP backbone. For ResNet, it's attention pooling. For Vision Transformer, a VIT, it's a linear projection.
And its job is?
To finalize the feature refinement. The output is what they call the enhanced feature, ZE. This enhanced feature is then passed along to the next modules, like ICD.
Okay, MAF sounds like a clever way to get a richer visual input. Now, the core, it seems. ICD Interclass Deconfusion. How does this module actually do the deconfusing?
Right. ICD is where the main action happens regarding the Logits. It takes the original zero-shot Logits, SCSI, but it also uses that enhanced feature, XI, from MA.
Ah, so the improved visual feature helps guide the deconfusion.
Precisely. It uses XI as prior information, and the structure is key. It uses a residual learning approach to learn and subtract the confusion.
Residual learning, like ResNets. subtracting something out.
Kind of, yeah. It uses 3 adapters inside: EICD A1, EICD A2, and EICD A3.
Okay, break those down. A1.
EICD A1 looks directly at the initial zero-shot logits, SCSI, and tries to learn confusion patterns just from those predictions.
And A2.
EICD A2 looks at the enhanced feature, Xi from MAF. It learns potential confusion based on the visual input itself.
So one looks at the prediction, one looks at the image evidence. What about A3?
A3 takes the outputs from both A1 and A2 and learns to combine that information. It jointly figures out the confusion pattern using both the initial guess and the better visual context.
So A3 is basically learning to predict that noise term, A's we talked about, but using more info.
Exactly. It's learning an informed estimate of the confusion. Then, the output of A3 is subtracted from the original zero-shot logits, SCSI.
Ah, the residual subtraction.
Yep. That gives you the ICD Logits, SICDI. The paper has the equation. By learning and removing the estimated confusion, the idea is you're left with logits that separate the classes more cleanly.
That's really neat. It's like saying, okay, CLIP, your first guess was a bit mixed up between these two, but looking closely at the image via MAF, we can correct that ambiguity.
You got it. It leverages CLIP's initial knowledge but refines it using these learned confusion patterns, informed by better features. This boosts adaptability for new domains, especially in few-shot.
Okay, MAF gives enhanced features, ICD cleans up the logits. What about the last piece, ALF Adaptive Logits Fusion?
ALF's job is to combine the results smartly. It takes the deconfused logits from ICD, SICDI, and also considers the logics you'd get just from the enhanced MAF features, SMAFI. How are those calculated? They're just obtained by passing the enhanced features I through a simple MLP classifier. So it represents a prediction based purely on the improved visual features.
Gotcha. So ALF combines the ICD prediction and the MAF prediction. How?
Adaptively. That's the key. It doesn't just average them or pick one. It uses another small module, an IA generator.
Alpha generator.
Yeah. It takes the enhanced features I as input and generates a weight, alpha. This weight determines how much influence the MAF logits get, and 1xScience determines how much the ICD logits get.
Whoa, so the image itself dictates how to best combine the two prediction sources.
Exactly. The final output is SALFI, calculated using this adaptive weight O. It lets the model lean more on the visual features if they're very clear, or more on the deconfused logits if maybe the visual information is still a bit ambiguous.
That's quite sophisticated. It adjusts the strategy based on the input instance.
It allows for dynamic balancing.
Okay, quick recap on training then. Cross-entropy loss apply to MAF, ICD, and ALF outputs.
Yes, supervising all 3 stages.
And those crucial similarity losses on MAF and ICD outputs compared to the original zero-shot logits.
Correct. LMAF SIM and LICD SIM, essential to prevent overcorrection and keep things grounded in CLIP's knowledge. They train all the parameters in the adapters, MAF, ICD, alpha generator, this way.
All right, the moment of truth. Does LDC actually work? Let's get into the experiments. They tested on 11 benchmarks, which is pretty comprehensive.
It really is. A good mix: ImageNet, Caltech 101, flowers, food, pets, cars, aircraft. Even satellite images with EuroSI2 and textures with DTD covers a lot of ground.
And they tested across different numbers of shots, right? 1, 2, 4, 8, 16?
Yep, the standard few shot settings.
Yeah.
From really tough 1-shot up to 16-shot.
Okay, how did LDC stack up against other state-of-the-art methods? What did Table 1 show for ImageNet?
On ImageNet, which is obviously a major benchmark, LDC hit 66.63% accuracy in the 16-shot setting. That was a 0.24% improvement over the previous best.
Okay, 0.24%. Modest, but on ImageNet, any gain is hard-won, right?
Absolutely. It shows the method is competitive at scale, but the average results across all 11 datasets in Table 2 are maybe more telling.
Right, the overall picture. What did that look like?
There, LDC showed consistently strong performance across all the K-shot settings. For 16-shot, the average accuracy was 79.78%. That's a more significant jump, 3.60% better than a strong baseline called protocelial PF.
A 3.6% average improvement is definitely solid.
Yeah, and Figure 5 breaks it down dataset by dataset. You see LDC doing really well pretty much everywhere, but especially shining on datasets like Euroset, FGV Carecraft, Stanford Cars, UCF 101.
So particularly good on those fine-grained or maybe slightly domain-shifted datasets.
Seems that way. It suggests the deconfusion mechanism is really helping, where distinguishing subtle differences is key.
Makes sense. Now, what about robustness? They checked performance on out-of-domain data, too. That's always critical.
Super important. They trained on ImageNet 16-shot and tested on ImageNet V2 and ImageNet Sketch. Table 3 has these results.
Additive.
On ImageNet v2, which is like a slightly different version of ImageNet, it did pretty well, showed good robustness with both ResNet and VIT backbones.
Okay, handles minor distribution shifts. What about ImageNet Sketch?
That was less impressive. Performance dropped off quite a bit there.
Which is still surprising, maybe. Sketches are visually very different from photos.
Exactly. CLIP is trained mostly on natural images. The struggle with sketches shows that even with LDC, handling really large domain gaps where the visual style is completely different is still a challenge.
So effective for similar domains, but big visual shifts are still tough. An area for future work.
Definitely. It tells us something about the limits of current transfer learning, even with these sophisticated methods.
To really understand why LDC works, they did ablation studies, right? Picking apart the components.
Yes, extensive ablations. Tables 4 through 8 detail this. Table 4 looks at the impact of each main module: MAF, ICD, ALF.
What was the biggest contributor?
Overwhelmingly, the ICD module, the Inter-Class Deconfusion part. Adding that gave the biggest accuracy boost by far for both ResNet and VIT.
Really validates their core idea of tackling the confusion directly.
Absolutely. MAF also added a significant improvement, showing the value of those multi-level features. And ALF provided another small but consistent gain by adaptively fusing the Logits.
So ICD is the star, but MAF and ALF play important supporting roles. Did they dig deeper into MAF?
Yep, Table 5. They found using more feature levels from the encoder generally helped. Interestingly, that specific weighted fusion scheme, 0.1, 0.20, 0.3, 0.4, actually did slightly better than equal weights or even the Learnable fusion in their tests.
Sometimes simpler is better.
It seems so here. They also showed the projector component in MAF mattered too.
What about ablating ICD itself? Table 6.
That showed two key things. Using the enhanced feature, InSci, from MAF as prior info for deconfusion was definitely beneficial. And the residual structure, the subtraction part, also contributed positively to the results.
So the design choices within ICD were well justified. And ALF, Table 7.
Confirmed that the adaptive fusion was better than just using ICD Logits, just using NAF Logits, or using a fixed combination. Adaptivity helps.
Finally, the loss functions. Table 8.
Crucial findings there. Removing the similarity losses, LMAF sim and LACD sim, caused a big drop in performance.
So that regularization preventing over deconfusion is absolutely essential.
Definitely. You need that balance between fixing the confusion and preserving CLIP's powerful prior knowledge.
Okay, so wrapping up this deep dive, LDC seems like a really solid, well-motivated method. It addresses a clear problem in few-shot learning with CLIP.
I think so too. The results are strong, especially the average across diverse data sets. Modeling and removing that interclass confusion directly in the Logits, supported by better features from MAF, it's a powerful combination.
And the architecture seems well thought out, with each piece contributing. The robustness to moderate shifts is also encouraging.
Yeah, it's a definite step forward. The limitation on ImageNet Sketch is important to note, though. It highlights where more research is needed for handling those really drastic domain gaps.
Absolutely. Which brings us to a final thought for you, our listener. The core idea here, identifying a specific failure mode, like interclass confusion, modeling it, and actively correcting for it is really interesting. Could you apply this kind of error modeling and correction thinking elsewhere? Maybe in NLP tasks where models get confused by ambiguity, or other vision problems with specific biases?
It's a great question. Thinking about how to model and subtract specific noise or bias terms in model outputs, that could be a really fruitful direction in lots of areas.
Something to definitely mull over for your own work. How could you perhaps adapt this LDC principle?
Definitely food for thought. And if you want to get your hands dirty with LDC itself, the authors have made the code available on GitHub.
Oh, that's great. Where can people find it?
The repository is at github.com, Lishuo 1001 LDC. That's Lishuo, Lishuo 1001/LDC.
Perfect. Great for anyone wanting to experiment or build on this work. Well, this has been a fascinating look at Logits DeConfusion. Thanks for joining us on the deep dive.